Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called TotBlocks. In this video, we'll explore the Pyroxene Group and its polytypes, and then use TotBlocks to construct their crystal structures. The word pyroxene comes from a combination of the Greek words pyros, fire, and xenos, stranger, and was originally used to describe crystals in lava flows that were considered to be accidentally included in the mix. Now, we recognize that pyroxenes are among the first crystals to form when a lava begins to cool down and become solid rock. The Pyroxene group includes minerals such as andesite, ferricilite, as well as augite, diopside, aegirine, and spodumene. Spodumene is an important ore mineral for the critical element lithium, which is used to make the lithium-ion batteries found in phones, cameras, and electric vehicles. The Pyroxene group consists of single-chain width modules which are connected by pyroxene-type linkages. Like other modular rock-forming minerals, the stacking of O modules in the pyroxenes leads to the development of structural varieties, or polytypes. There are three main polytypes of pyroxenes: the clinopyroxenes, which crystallize in the monoclinic system, as well as the orthopyroxenes and protopyroxenes, which crystallize in the orthorhombic system. Let's dive into the clinopyroxenes first. The clinopyroxene structure consists of TOT rod modules that use only O+ modules, which results in a stacking offset along the length of the rod modules and produces monoclinic symmetry. Here's the full structure of a clinopyroxene. Now we'll take it apart. To learn how to build the component TOT modules of this structure, take a look at the Assembly of TotBlocks video in this series. To construct the clinopyroxene structure, connect one single chain width TOT module to a second single chain width module such that the T- module of the first is joined to the bottom of the O+ of the second. Then a third single chain module can be connected so that the T+ of the first module is connected to the top of the O+ of the third module. This pattern can be repeated as needed to extend the structure. A fourth T+ module is joined to the second and third T+ modules to complete the structure. Now let's take a look at the orthopyroxenes. Here's the full structure of an orthopyroxene. The orthopyroxene structure consists of corrugated TOT rod modules that contain O+ modules, alternating with corrugated rows containing O- modules. This alternation results in a negation of the lengthwise offset and leads to orthorhombic symmetry. Now we'll take it apart. To construct orthopyroxene, 4 single chain with TOT modules must be made. 2 of these modules will use O+, and 2 of these modules will use O-. Using a TO- T module, connect the T- to another TO- T module at the bottom of the O-, and then connect the T+ to the top of the O+ module of a TO+ T module. Finally, a fourth TO+ T module is joined such that the T+ of the third module is joined with the top of the O+ of the fourth module. This pattern can be extended to complete the structure. And we will do 2 of these iterations here. Last but not least, there are the protopyroxenes, which are the less common, high-temperature pyroxene polytypes. Here's the full structure of a protopyroxene. The protopyroxene structure consists of rows of TOT modules with alternating O+ and O- modules. This alternation results in the negation of the lengthwise offset and leads to orthorhombic symmetry. Now we'll take it apart. Similar to orthopyroxene, protopyroxene can be constructed with 4 single-chain with TOT modules, 2 O+, and 2 O-. Specifically, using a TO plus T module, connect the T- to the bottom of the O- of an TO- T module. And the T+ to the top of the O- of the TO- T module. The final TO plus T module will be connected to the structure by linking its T- to the base or the bottom of the O- of the 3 modules. This pattern can be repeated as necessary to extend the structure. And here we'll do another iteration. So these different polytypes of pyroxenes are similar because they use single chains of silica tetrahedra with pyrosyl linkages, but they differ based on how their O modules are stacked. In terms of the crystal chemistry of the pyroxenes, silicon fits into the tetrahedral T sites, whereas magnesium, iron, and aluminum can fit in the M1 octahedral site. There's also an M2 site that borders the O modules and can incorporate calcium and sodium, as well as magnesium and iron. We can use the difference in crystal system to differentiate between orthopyroxenes and clinopyroxenes in thin section. Every mineral has a specific orientation in cross-polarized light, where light doesn't bend or change directions when traveling through its crystal structure, known as extinction. For pyroxenes, the best grains to look at will be those with only one clear set of cleavage planes. Orthopyroxenes have straight or parallel extinction. The mineral grain will turn black when the cleavage planes are oriented vertically or horizontally in the field of view. In contrast, clinopyroxenes display inclined extinction. The mineral grain will turn black when its cleavage planes are angled and not oriented vertically or horizontally in the field of view. Differentiating between clinopyroxenes and orthopyroxenes is important because the M2 site in clinopyroxenes is larger than the M2 site in orthopyroxenes. So the clinopyroxene structure can accommodate more calcium and sodium than the orthopyroxene structure. In other words, the polytype of pyroxene present can tell us more about the chemistry of a rock. In this video, we've learned about the Pyroxene group and its polytypes, and we've seen how single chains of TOT modules can be linked together to form either monoclinic or orthorhombic crystal structures, depending on the stacking of the O+ and O- modules. We've also looked at how these different crystal structures affect the optical properties of these minerals when examined in thin section.